Hello again. Let's consider another example of a monad, and this time let us venture outside the safety of the category of sets to the category of preorders. So point being that this is not something you can do in Haskell, where everything always happens at the category of sets or types and functions. Right. So I want to consider an example that occurs naturally in mathematics. So I want a functor on the category of preorders, and I'm going to call this functor lift for a reason that I'll tell you in a moment. So it should take a preorder and give me back another preorder. And the idea is that if we take our preorder P like this, then I'm going to add one more element to this preorder. It is usually denoted bottom, not to be confused with falsity. And I'm going to say that this element is smaller than all the elements in P. So this is going to be my new lift of P. Right, so I'm lifting P up above this new element, which is at the bottom. And if P didn't have a smallest element, now it does, right? So that seems like it could be a functor at least, because if I have another one of these, so I'm lifting up some Q, then there is an obvious monotone map between these two things, right? Where I'm sending, if I have a monotone map from P to Q, then I can use that on P to send that to something in Q, and I'll just send the new bottom element to the new bottom element. So that's at least a functor, and this is going to preserve identities and composition, because this map up here is going to do that. Okay, so the question is it a monad? So what does it mean for it to be a monad? It means that we should have an eta, which goes from P to lift of P, right? But there is an obvious way to include P into this. We just send everything up here, and it's going to be order preserving, because we keep the order up here, right? And okay, so we have an eta, and we also need to have a mu, which goes from the lift of P down to the lift of P. So what does that mean? It means that if I have P like this, and then I lift it up, and then I take that, and I lift that up, then I should be able to go down to just lifting up P, right? But I think I can do that as well. I'm going to send this bit to this, and then I'm going to send the remaining bottom element to the bottom element here, right? And because this is the smallest thing in both of these, this is also going to be order preserving. Okay, so I think I can define both an eta and a mu, which means that I have a chance of actually constructing a monad. Right, so let's see if I can do this in Agda. So here we are. I am defining the lifting as a data type, where I have a way to include the old things, and I have a new bottom thing, right? And then I have to define an order on this. So I'm saying that if P was smaller than P prime in the original preorder, then eta of P is smaller than eta of P prime. And that very conveniently tells me exactly that eta is order preserving, right? But it's also what I need in order to keep the old order on the old P, right? And then here I'm saying that for every x, the bottom element is smaller or equal to x, right? Okay, so I've defined an order, but I have to show that it's reflexive and transitive. So let's do that. So I'm going to do that by looking at the x. It's either an eta or the new bottom element. Okay, if it's an eta, then I need to show that eta P is smaller than eta of P. Well, eta less than will do that if I know that P is smaller than P, But I started with a preorder, so I know that P is reflexive. Let's see what went wrong here. So it's implicit. Right. And for bottom, I need to show that bottom is smaller than bottom, but I know that bottom is smaller than everything, including itself, so that's fine. Okay, what about transitivity? So here I have two proofs P and Q, and I need to combine them. So let's look at what P and Q could possibly be. They're either both etas. Let's call this one P and this one Q. Or the first one is a bottom. So in this case, where they are both etas, then again I can use the inclusion of eta, like the source preserving, right? And then just use the transitivity of P and Q. And otherwise here, it's easy to just use the bottom, because this proof was bottom, that means that the x that I want here must have been the new bottom element. Okay, and it's also not hard to define this map function, right? You just apply the f in the case of the eta, and if it's a bottom, you keep it the same. So I think that's all we need to define this functor now. Let's see. We need an action and objects. That's going to be, let's see. So we get given a preorder P, and this takes a while. Okay, we get given a preorder P, and now we have to construct the preorders. The carrier is going to be lift the carrier of P, and the order relation is going to be the order relation we defined. And reflexivity is the reflexivity proof that we defined. Transitivity is the transitivity proof that we defined. Okay, but we also have to show that this order relation is propositional, right? That remember that we asked for our preorders to not have any computational content in these order proofs. So let's see if we can do that. So we get given two proofs P and Q, and we have to show that they are equal. So let's see what these P and Q could possibly be. Well, it could either both be inclusions of the other preorder, in which case we know that that one is propositional. So that shows that P equals Q, so if you use a con of eta less than, that should take care of that. Otherwise we know that they are both bottom, in which case they are of course equal. So that was okay. Okay, and now we need the F map. That's our map lift. So that's the map part of it. But we also need to show that map lift is monotone, right? So we get given x and y, and the proof that x is smaller than y. And we have to show that the result of map lift of x is smaller than the result of map lift of y. So let's look at this proof and see what it is. It's either an inclusion from the original preorder, in which case we should be able to use the fact that f is monotone, together with eta less than, I hope. Yes. Or it's a bottom proof, which means that this element was bottom, and then maplift is preserving the bottom. So this should just be bottom. Okay, we also need to show that this preserves the identity. And we had a way to show that monotone maps are equal. It's enough that they're equal on the function component. Okay, let's use function extensionality. Okay, so we get given an x. Right, so I'm going to use a pattern matching lambda here. Right, that's why I put these curly braces on the outside. So normal lambda can't pattern match, but if you put the curly braces, then you're allowed to pattern match on this lambda. So now I'm going to pattern match on the x, and that's going to make this maplift reduce. Right, so in this case, it's easy, and in this case, it's easy. So I only need to match on the x so that I get this to reduce, and then in both cases it's easy. And similarly here, x do something. Let's use a pattern matching lambda. Okay. All the cases are easy. Right, and the reason I could get away with a pattern matching lambda here, by the way, is that there are no recursive calls in this thing, right? So I don't need to call myself, so I can use a lambda. I don't need to do any recursive calls in this proof. If I did, then I would have to name this thing and use a lemma instead. Okay, so now let's see if we can actually define this monad. So we have a functor. So we're going to use that as the functor. And now here we need return. So to transform this for a given p, we need a monotone map from p to the lift of p. Right. So the underlying function should go from the carrier of p to the lift of the carrier of p, but that's what eta is doing here. Right? That's why we named it eta in the first place. So we can use eta for that. And the fact that it's monotone, well, given x and y and the proof, well, we need that eta of x is smaller than eta of y. That's exactly what eta less than tells us. Right. So that was easy. Is it natural? Well, let's see. Okay, well, here we have to show that two monotone maps, that is preorder morphisms, are equal. So let's use EQ monotone. Okay, well, this looks like it's just true. Okay, what about the join? So here, for a given p, here we need a monotone map from the lift of p to the lift of p. Right. So let's see, the underlying function should be like this. So we get given x, say, let's look at the x. If it's an inclusion of a lift, then we can just give that back. And if it's the bottom element, then we can map that to the bottom element. Right. Okay, we have to check that this is monotone, so we get given x and y and a p. And what can we possibly do? We have to look at this p. And two cases, it can be an inclusion or it's bottom. If it's an inclusion, then we have the P we need. If it's bottom, then we started with a bottom and we are sending it to a bottom. So we can keep using the bottom proof. Okay, is it natural? Well, it's an equation between monotone maps, so let's see. Okay, this doesn't look immediately the same, right? So let's use function extensionality. Get given an x. I'm going to pattern match on it next. I'll use a pattern matching lambda. Okay, two cases. In this case, everything is reducing, and now it is obvious. In this case, everything is preserving bottoms, and that's also obvious. Okay, and then here we have to prove the laws. So without thinking too much about it, it's an equation between monotone maps. It's an easy equation on the functions. This is also an equation between monotone maps. Not as easy. Let's use function extensionality. Pattern matching lambda to the rescue. It's actually a pattern match on it. Okay, now things are reducing and life is good. And here, finally, it's another equation between monotone maps. Is it obvious? Maybe this? No. So let's use function extensionality. Pattern match on the x. And now it's obvious. Okay, so that's an example of a monad which is not in the category of sets, right? Which is adding this extra element to a preorder. So there's lots of examples like this if we just leave the safety of set behind. So there's lots of examples in set, of course, but mathematics is full of monads.